Hello everyone, today we will demonstrate how the abstract mathematical concept of trees from our discrete structure syllabus are applied in real-world digital environments. My name is Ding, and now we will start our presentation. Trees are one of the most important data structures in discrete mathematics and computer science. Mathematically, a tree is an acyclic connected graph, meaning there is only one unique path between any two nodes. It features a unique origin point called the root, which branches down into parents and child nodes, eventually ending at terminal points called leaves. Unlike linear structures, trees organize data hierarchically. This structure allows information to be organized efficiently and clearly. This diagram visually shows the difference between a tree and a graph. According to the edge-vertex theorem, a tree with n vertex must contain exactly n minus 1 edge, and there must be exactly one unique path between any two vertices. If an extra edge is added, a cycle is formed, and the structure is no longer considered a tree.
Hi, my name is Sofarisha Binti Ahmad Shukri, and now we will look at our first system, which is the file system. Every OS, such as Windows, Linux, and Mac OS, organizes their storage using a rooted ordered tree, which means that you have one starting point that branches downwards with no loops. So for example here, the root is C:\/ for Windows usually. Folders are internal nodes, files are leaf nodes with an order degree of 0, which means they have no children. And also the edge-vertex theorem tells us that for any tree, the number of edges equals number of nodes minus 1. This is diagram 2 from our report. To start with, we have C:\/ which is the root node. It is also the only node that have no parent and no incoming edges. From here, we branch into Windows, users, and program files, which are known as internal nodes or parent nodes. Inside users, we have Farisha. Inside Farisha, we have documents. And inside documents, we have report.pdf and notes.doc. These are the leaf nodes. They have no children. And now let's verify the edge-vertex theorem. And if we count, we have 14 nodes, so we should have exactly 13 edges. And so this confirms the edge-vertex theorem, and we have now a valid tree structure. This is exactly how the OS finds report.pdf. The first step is that we must begin at the root, which is the C:\/. The second step is we need to search within the root for a child named users and then move into it. The third step is we need to search within the users for Farisha and move into it. The fourth step is we need to search for the documents, and last step we will find the report.pdf in the folder. And now notice that at each step, the system only searches within the current folder, and it will ignore the windows, the program files, and everything else. And this is exactly the efficiency of trees. And let's say if we have a flat list of 1 million files, you need up to 1 million comparisons. But however, with a tree, you need only around 20 steps, and that is O log n versus O n. To summarize, System 1, which is the file system, is not just organized like a tree. It is a tree, but it is implemented through structures like the NTFS master file table in Windows. The three key impacts are: first, O log n search efficiency. It means that finding any file in millions will take only a handful of steps. Second, guaranteed unique file path. The uniqueness property means every file has one unambiguous address, which is essentially for file permissions and security. Third, reliable loop-free traversal. Because the tree is acyclic, no system operations can get stuck in an infinite loop.
My name is Tan-Su-En, and next time we are talking about our syntax system. We will look at natural language processing or NLCP syntax parsing. To help computer understand human language, we use a syntactic parse tree, which is a real-world application of a router label tree. Mathematically, this structure relies on strict contrast. It is an acyclic graph, meaning there are no closed loops, which allows the computer to analyze sentences deterministically. It also follows the uniqueness property, where there is exactly one path from the root to any given word. Finally, it strictly obeys the edge vertex or theorem, which detects that the number of edges is always the number of vertices minus 1. Here is the diagram representation for the sentence. The student passed the exam. The root node labeled S for sentence has an in degree of 0. It branches out into internal nodes representing grammatical components like noun phrases, NP, and verb phrases, VP. The actual words like the and student are the leaf nodes at the bottom, which have an out degree of 0. We can mathematically verify these three using the edge vertex theorem. As you can see at the bottom, there are 10 vertices and 9 edges, perfectly satisfying the formula E equals to n-1. So how is this implemented in systems like Google Translate? Let's do a quick demonstration. Google's NLP engine uses a context-free grammar parser to build the source tree we just looked at. Then it maps the subtrees individually. Notice the automatic word order restructuring here. In English, the structure is determiner plus noun, the student, but in Malay, the root is noun plus determiner. Because the system isolated this as specific noun phrase subtree, it automatically flips the words to belajar itu. Before recombining it with the rest of sentence, this prevents messy, direct word-for-word translations. The major impact of using this discrete structure is the elimination of ambiguity. Take the sentence, I saw the man with the telescope. Do I use a telescope to look at him, or did the man own a telescope? Human language is ambiguous, but math is not. Because of the uniqueness property of trees, the parser is forced to choose exactly one branch path, ensuring the translation engine commits to a single consistent interpretation. Furthermore, tree-based parsing operates at a highly efficient logarithmic time complexity, making real-time translation possible even for incredible complex sentences. To conclude, trees are among the most crucial data structures in modern digital systems. They provide a highly logical way to organize and process hierarchical information. In System 1, we saw how file systems use trees to enable fast file retrieval and guarantee unique file paths. In System 2, we saw how NLP uses trees to resolve linguistic ambiguity and restructure grammar for accurate translations. As digital systems grow in scale, the mathematical integrity of tree structures will remain essential to computer science. That's all from us. Thank you for listening.